this is about my project in mobile and pervasive computing coursework. So what we have done is like benchmarking lab automation vision classification models on embedded hardware platforms which doesn't have much of the resources. So modern large scale lab automation continuously relies on human in the loop oversight, and there are multiple robotic and mobile units which actually asynchronously communicate over secure networks and can actually require uninterrupted sources of network compute and service access. And we have found out we have chosen the problem of image classification. So across the lab automation scenario, we have identified that YOLO-11 nano, small, and large models with parameter size 2.8 to 6.7 and 29.6 are widely used across the real-time image classification in lab automation setup for error handling and automated error recovery. For real-time real-time vision or lab automation, the workflow should actually target less than 100 milliseconds. And we should consistently monitor the P95 like the latency, which is kind of outlier to the processing. So basically, what we have done is like we identified that for image classification across all the models, across all the model parameters, if it is a float 32, if it is a int 8, or if it is a anything like that, the accuracy is consistently over 95%, which is more than our use case. The only bottleneck that lies is the latency. So for the latency, what we try to do is like we have a Tachyon onboard single-board computer, which we think that can actually help in the lab automation process, and we try to offload the we try to do the inference int8 inference on the 12 TOPS Qualcomm Hexagon 770 NPU and get the data. So as we are seeing that the mean latency is 9.53 and we have a P95 of 10.78, which actually meets our need. And also we have tried to use the onboard CPU on this device and try to do an inference on the float 32, full-blown float 32 and a quantized full int8 quantization. And we got the inference latency of 40.01 and 17.17 with the P95 well below the 100 millisecond range. And another scenario what we try to do is like which shows in our system architecture is like we have a database of image or a live camera image. That image actually gets sent as a frame to the our Tachyon is acting as a client, and this Tachyon is actually sending the frame to the cloudlet, which is the edge server. So cloudlet is basically a small scale data center located at the edge of a network, and we are using a CMU Wi-Fi network, and we are using a Gabriel networking framework, which is developed by the CMU Living Edge Lab. And we are sending the frames, getting the statistics, and getting the overlay back and showing it in a local display. And for that, we are getting a mean latency of 76.72 with P95 going beyond 100 milliseconds slightly. So for this, I can show a demo, basically how it will happen. So first thing, we will try to exercise the NPU here for the live inference. So first, it will show whether we want to detect a droplet. So we space press and we show the camera. We show the camera and the droplet is detected for this still image. There is a thing, we have collected all the training images here. The thing is that it is an open set classification problem because we were not we are not doing the machine learning in a OT2 robotic handler real-time system. So that is why the classification problem is an open set classification, and it has some issues in recognizing unknown data set, which is multiple. So the droplet present is accurately detected within 13.34 millisecond, and the temperature, the thermal zones are showing for the NPU. And now I will show the droplet absent. So the droplet absent is accurately captured. And the droplet absent is accurately captured, and the NPU latency is 9.44, and the temperature is rising on the onboard CPU. For the next set of tasks, we will try to stress test this NPU, which is which is an unknown image. So I can point a camera to anywhere, basically. So the temperature, if you can see, the temperature is continuously rising in the neural signal processor thermal zones, and it will rise to about 47 Celsius, and we will capture the image. What is happening here is like what is happening here, we can see that the NPU is once the temperature is rising, the NPU is actually thermally throttling the clock because of the dynamic voltage frequency scaling, and that is why the NPU latency is kicking up to a high range rather than our graph. So that is why we need to have a onboard cooling on this on this Tachyon. So it will rise to 47, and you can see. So as you can see, there is spikes in the NPU inference latency. Yeah, so this is about our demo, and it will rise and it will capture one image and it will show all the three images in one window. And apart from that, there is another demo which will show the cloudlet offloading, the inference server offloading, which I can go through just now. So this is the one. So if you see, the cloudlet inference is on the best model, which is about showing 39.82 latency. This is the mean and the standard deviation, and the P95 is not going beyond. But because of the Wi-Fi latency and the Gabriel network, it is sending the frame and giving the stats back. So that is why the latency is kind of high. So as per our recommendation, we recommend that we should be leveraging the onboard xPUs or the NPUs on the board, like the CPU, mostly the NPU, if we have for a resilient short-term fallback, in case the Tachyon has an active cooling mechanism, and for long duration alternative for higher peak accuracy image classification tasks real time, we should offload it to the server like the cloud. Yeah, this is about my demo.